This will be lesson 3 of chapter 3, and here we will talk about something called isotopic abundance. This first word refers to an isotope, remember, which is an atom of the same element that has a different number of neutrons. And we'll describe exactly what we mean by abundance. The picture that you see here is a bottle of chlorine gas. It's nice and pale green. And recall that in any amount of chlorine, or any element, what you have is you have different types of chlorine atoms. And these are called isotopes. And that's what we'll take a look at. So we've shown you a few of these concepts. So we've shown you the atomic number. And on the periodic table, each element is represented by a block like this. On top of the symbol of the element is shown the atomic number. Remember, this is the number of protons in the element. And the other number that we'll spend today's lecture on is this atomic mass. This is the bottom number, or the decimal number. Every element shows this decimal number, and this is the atomic mass. We've introduced the atomic mass in terms of units of AMU. Remember, this is called the atomic mass unit. So this is how heavy each atom, on average, is. So each atom of chlorine has this mass, 35.453 AMU. And we'll take a look at what this number means. This number will be related to the isotopes of chlorine. There are two isotopes of chlorine, chlorine-35 and chlorine-37. And remember, the way we write isotopes is we put the mass number of the isotope, and the mass number tells us the number of protons plus neutrons in it. So the two chlorine atoms differ in their number of neutrons. They're both chlorine, they have 17 protons each, but their neutrons differ. And these two isotopes are combined together in a certain way to give you this atomic mass. And that will be the central idea of today's discussion. So the atomic mass on the periodic table is what is called the weighted average of the different isotopes of that element. So each element has a bunch of different isotopes, and it has different amounts of these isotopes. In other words, for the element sulfur, there are 4 possible isotopes. There are 4, you can say, varieties of sulfur out there. Sulfur-32, sulfur-33, sulfur-34, and sulfur-36. So these are all the isotopes that exist out there in the world. If you take an amount of sulfur, you'll find all 4 of these present. Now these will be present in different amounts, and that's what we're going to talk about here next. So we're going to actually consider the element lithium to find out how we determine the atomic mass. Now lithium has 2 major isotopes. The first has a mass of 601 AMU, and the other one has a mass of 701 AMU. This will be lithium-6, and this will be lithium-7. Now, the first, the lithium-6 variety, has an abundance of 7.59%, and the second has an abundance of 92.4%. What we mean by this abundance number is what percent of all the element out there is of that isotope. So for all the lithium that you find, about 7.5% of it will be of the 6 variety, about 92.4% will be of the 7 variety. Any amount of lithium you find, they will be broken down in this percent way. And if you take a look at the periodic table, what you'll see is that the mass of lithium on the periodic table is listed as 6.94. In fact, here it is. And the question is, how is this number obtained from the isotopes of lithium that are present in the world? So how was this number calculated? How was this number obtained? And it has to incorporate, it has to put into it both lithium-6 and lithium-7 from what's existent in nature for lithium. So summarizing this is the next slide. Here we have these 2 isotopes of lithium, lithium-6 and lithium-7. Again, here are their masses, and here are the percent abundances in the world. What we're going to do is we're going to average these 2 numbers, and the averaging will be similar in the way that your grade is averaged. Remember that your grade has a homework component and a test component, but the test portion of your grade is 70%, whereas the homework is only 30%. which means the tests weigh much more heavily on your overall grade. A similar thing will happen here. Lithium-7 will weigh much more heavily on the overall mass of lithium because it's more abundant. In fact, if you take a look at lithium's mass on the periodic table is closer to the 7 than it is to the 6. In fact, we've just seen it. It was 6.941. Notice it's closer to the 7, and that's because most of it is lithium-7. It weighs, the lithium-7 isotope weighs much more toward the total. Here's the actual equation that we're going to use to calculate percent abundance, and it looks like this. You'll take the percent abundance of the first isotope divided by 100, and this divided by 100 undoes the percent. Here we will undo percent. That's why we're dividing. Remember, in order to get percent, you multiply by 100. To undo it, we divide by 100. You multiply that number by the mass of the first isotope, and then you do the same thing to the second isotope. Take its percent abundance, divide by 100, multiply by its mass, and then you'll add the two together. If there's a third isotope, many elements have 3, 4, 5, 6 isotopes. You keep doing this, and then you add all of them up. And we'll actually use this equation here in the calculation. So take a look at this equation, see if it makes sense. Your grade is calculated exactly the same way. Your test grade here, whatever you got on your test grade will be multiplied by its percent abundance. So let's try that. Let's go ahead and try an example of this. Here it says calculate the atomic mass of lithium from the data given above, 2 slides above. So let's do this. The percent abundance, we took the percent of the first isotope, which was 7.59%, divided by 100. We multiplied by that by the mass of the first one, which was 6.01. Then we did the same thing for the second one. We had 92.4% over 100 times 7.01, and we added these two together. So here would be the setup. Let's go ahead and calculate these out. Let's go and put them on the side there. So if you do 7.59 divided by 100, go ahead and do this on your own, times 6.01, you will get yourself 0.45075. Since we have 3 significant figures, let's do 0.451. If we do the same thing to that second number, we get 92.4 divided by 100 times 701, we get 6.477. And then we will have to add these two numbers. And adding these two numbers, we should get, go ahead and do this in your calculator, 6.928. And this is our answer. Now, because we have 3 significant figures here, we can only say 6.93 for our final mass. And if you take a look, that actually matches pretty closely to what we have for the lithium on the periodic table. If you take a look at your periodic table, you should see lithium's mass be about 6.93. So this is how it is calculated. And I want you guys to try one of your own. Go ahead and pause the video and try doing the exact same thing. Here you have 3 isotopes, but you'll do the same thing, except you'll do it with 3 of them. Let's finish up with this problem then. And this is essentially doing the same thing backwards. Here it says, using the information below, find the percent abundance of chlorine-37. So chlorine, just like lithium, has, and we began with a picture of chlorine, so this is appropriate for us to finish with chlorine as an example. Chlorine has 2 isotopes, like lithium. The first is chlorine-35, the second, chlorine-37. Their masses are given to us here, and their percent abundances are given here. Now, here we're asked to find the second percent abundance. In order to do this, we'll need to pull the mass of chlorine from the periodic table. If you take a look at chlorine in the periodic table, it will say that chlorine, which has 17 protons, has a mass of 35.45. So we're going to see, we're going to use this number, the total number, to find out the percent abundance of the second isotope. I'm going to use the same equation, except I'm going to string it out. Remember, the equation said that you take the mass of the first times its percent abundance plus the mass of the second times its percent abundance. So I'm going to string this out in one line. So we're going to take the mass of the first isotope But because our equation began with the percent abundance, let's go ahead and do that. Let's put percent. So I'm going to just write out the numbers. So we got percent of the first, which is 75.77 over 100, multiplied by the mass, which is 34.9688, plus the percent of the second. And we're going to get a little tight here. I'm going to, because we're getting a bit tight, let me squeeze it in a little better here. Apologize for the, let's try that again. 75.77 over 100 multiplied by 34.9688 plus, now the percent abundance of the second one we don't know. So I'm going to put x divided by 100 here. So this will be x divided by 100, just like I have the 75.77 times the second one, which is 36.9659, and then this will equal our total, which is from the periodic table, which is 35.45. And now we're going to use algebra to find x. This is going to be a bit tricky maybe if you haven't seen this sort of calculation. This is really just from algebra. So go ahead and let's combine everything here as much as we can. Let's multiply these numbers together. So 75.77 times 34.9688 should give us 26.49. Let's do 496 here, one more significant figure. Plus this is x over 100 times 36.9659 equals 35.45. Now in algebra, if you recall, what we'll do is we'll subtract this number here. Because it's being added, we'll have to subtract 26.496. We'll have to do the same thing here, 26.496. And then we'll end up with x over 100 times 36.9659 equals, and if you subtract those two numbers, you should get yourself, go and do this on your calculator, 8.954. Next, because we are multiplying by 36.965, we're going to divide by that to put it to the other side. So we'll divide by 36.9659. We'll have to do the same thing here, 36.9659. And then x is being divided by 100, so we'll have to multiply that by 100. I'm going to do it in one step. You can do it in two steps. But we're going to multiply by 100 here, do the opposite, so we'll end up multiplying by 100. This is essentially because we're solving for the percent, we're multiplying by 100 to get that final percent. So it's a bit messy, but these cancel out, and you got x equaling whatever this portion is. Let's go ahead and multiply that out and see what you get. So divide that by 36.9659, then multiply by 100, and you should get yourself x to be x equals 24.22%. And let's see whether that makes sense, whether it matches up. Notice that this number is about 76%, and this number is about 24%. 76 and 24 is 100%. So we did it right. So in fact, you could have gotten this answer really quickly by simply subtracting from 100 75.77, but we showed you how this equation, the percent abundance equation, works and makes sense. So hopefully you've enjoyed lecture 3 of this chapter 3.